let's move on to the Lewis definition. And we already started talking about this. As soon as we started using curved arrows, we were talking about Lewis acids and bases, whether we knew it or not. And even with the Bronsted-Lowry theory, I used curved arrows in order to show you how the electrons are going. So let's formalize this and talk about a Lewis acid as being an electron pair acceptor and a Lewis base being an electron pair donor. In Bronsted-Lowry, H+ was specifically the electron pair acceptor. We can go beyond that, though, with Lewis acids and bases. We won't always need to be transferring an H+. We could have just a pair of electrons that's attacking something else. So this Lewis acid-base model will really be the foundation for all of the mechanisms, pretty much, that we'll be drawing in this class. We're going to find an orbital with a lone pair of electrons and some sort of concentration of negative charge. And those pair of electrons will seek out a vacant orbital that's carrying some kind of positive charge to it. So that curved electron formalism will always go from the Lewis base to the Lewis acid. So when we're solving problems in this course, we're going to ask ourselves, where's the Lewis base? So where's the concentration of electrons at? And then where will those electrons be attracted to in order to form a product? So if we take a look at these compounds here, and there's BF3, what happens is this oxygen compound right here, that's the Lewis base. BF3 is the Lewis acid. Because boron, it's actually short of its octet, so it's sp2 hybridized, and it'll have an empty p orbital that these electrons from the oxygen can attack. So take a look at this major partial positive charge on the boron, symbolized by this bluish color around the boron. Take a look at the negative charge around that oxygen, symbolized by this red color. These electrons here from the oxygen will seek out that boron and will form a new bond. The new bonds do have formal charges to them now, but there is some favorability to this because now at least boron has a complete octet. Over here, boron just had 246 around it, so there's going to be a significant driving force for boron to find something nearby that'll be willing to donate some electrons to help it complete its octet, like that. So anything, really anything in an organic molecule with lone pairs on it, especially if it is an electronegative atom, like O or N, or even sulfur, right, can be Lewis base too. So identifying the lone pair of electrons, right, that's usually a lone pair that's not tied up in resonance, a lone pair that's available to go out and seek a positive sink of electrons, can be useful. So let me just draw you an example of one way that we're going to use Lewis theory in order to predict how reactions work. So let me make CH3O minus, so methoxide, the conjugate base of methanol, and I'm going to react it with CH3, C double bond O, Cl. Using Lewis theory, we should be able to figure out what reaction is going to happen here. I have a negative formal charge. That is going to be king to us in terms of Lewis bases. That is a major source of electrons. So one of these lone pairs here will be what we'll start with. Well, let's figure out what that'll be attracted to. Well, I have some electronegative atoms here that'll pull electron density away from that carbon. So here I'll have a carbon that is partially positive. The carbon of a C double bond O, really any carbon that's attached to oxygen or attached to chlorine, will carry a partial positive charge and will be really attractive to a pair of electrons from a Lewis base. So look what happens. Let's draw that a little better here. One of these lone pairs will attack that carbon, but the carbon already had 4 bonds, so we don't want to have a Texas carbon. We need to get rid of a bond somewhere. So a good way to do that is a lot like what we did in resonance. I'm going to take one of these double bonds, and I'm going to kick a pair of electrons that did make up that double bond up onto the oxygen. So what I've formed here is a new sigma bond between the O of our CH3O and the C that used to be on the C double bond O. So let's use a new color here to do the new stuff. So CH3O, here's our new sigma bond. I'll now end up with a minus charge on the O that used to be double bonded to that carbon, because remember we kicked a pair of electrons up onto there that used to be in the double bond. So right here, let's use my blue here. That's our new sigma bond. So very often in Lewis acid-base reactions, we form a new sigma bond, okay, by having the Lewis base having its electrons seek out a partially positive Lewis acid, forming a new bond. Oftentimes then something will get kicked off of that new atom that's formed. If that Lewis acid lacks an octet, like it did in boron on the last page, then we don't have to kick anything out. Then bringing it in just completes the octet. But if there is an octet on that atom, something has to leave off of the other side in order to make room for the electrons that are being added. So just have some basic understanding of finding the negative place, finding the positive place. Those electrons seek out the positive. That's what happens.